Okay, thank you very much for accepting my talk in the video format. So I'll tell you about a generalized cohomology theory for quantum contextuality. So in this talk, quantum contextuality is going to be state-independent quantum contextuality, which is formulated using linear constraint systems. And the goal is going to be classify operator solutions of linear constraint systems using homotopy, and eventually using generalized cohomology theory. So I will introduce a particular generalized cohomology theory, which is going to be useful in classifying operator solutions. A linear constraint system is essentially a linear equation over the ring of integers mod D. So it is specified by a matrix M, and there is the column B, and then if you want to solve this equation over Z mod D, you would be looking for a solution, which would be finding X. But in linear constraint systems, what we are looking for is more general than this. We are looking for operator solutions that consist of unitary matrices for a fixed dimension. So here UM is unitary matrices M by M matrices. And there are a couple of conditions on these matrices. First of all, they're supposed to be detorsion, meaning that the d power of these unitaries is equal to the identity. And they're supposed to pairwise commute for certain subsets of these matrices, which I'll tell you more precisely which ones. And there's a linear constraint, which is coming from this linear equation, which is turned into a multiplicative form. I will also tell you the precise form of this constraint. So today I'll tell you how to construct a generalized cohomology theory that can be used to classify operator solutions of linear constraint systems. So there are a couple of steps. So the first step is to construct a space of contexts. So I'll tell you what the contexts are in this specific talk. And there's a way to assemble all contexts in unitary groups into a space. And once we have this space, then we can interpret operator solutions as maps into this space from a certain from another space, which is called a topological realization. And there's a procedure that helps you to understand, to compute the homotopic classes of maps, which is called the stabilization. And this procedure eventually gives rise to generalized cohomology theories. And finally, I will tell you how a well-known example of Mermin square can be seen as a class in this generalized cohomology theory. Well, a nice question to keep in mind, it's a motivation to study these things, is to following question. So as it says, viability gap for odd local dimensions. So are there any linear constraint systems which admit an operator solution over the unitaries where m is greater than or equal to 2, but not over U1? So that means no scalar solution. This question is a motivating question for these classifications, because at the end I will tell you how to classify them, and then I will tell you how to compute these equivalence classes. But the question of whether these equivalence classes actually come from which corresponds to general classes in the generalized cohomology theory, come from actual linear constraint systems is an open question. So the contexts are going to be unitary matrices which pairwise commute, and detorsion, meaning that the d power is the identity. So these are the contexts that we are going to restrict to these throughout the talk, because it's for linear constraint systems we are looking at the operator solutions, and operator solutions are already satisfying these two conditions, so it's very natural to pick these as a choice of contexts. And there's a more compact way of thinking about contexts, which is thinking of them as group homomorphisms. So this group of integers modulo D, you can take n copies of it. So this is an abelian group, and you can look at group homomorphism. So once you look at the group homomorphism, you can evaluate on the generators of this Z mod Dn, and that way you can obtain an n tuple of unitaries. That will be your context. And the detorsion property and the pairwise commutativity is automatically built in once you say this is a group homomorphism. That's why it's a nice, concise way of talking about a context. And the linear constraint system more precisely is described using a hypergraph. So as I mentioned, it was initially described using this matrix equation. And we can turn it into a pair where H here is a hypergraph and tau is a function on the set of edges. So the set of vertices is going to be corresponding to the variable. So there will be vertices which are labeled from 1 to C, where C is the number of elements in the column. And the set of edges which are going to encode the rows. So they're going to be labeled by from 1 to R. So there's the number of rows in an incidence weight, which is going to correspond to precisely the entries of the matrix here. And the edges, more precisely, each edge is going to be given by the non-zero, by the vertices for which the corresponding row here has a non-zero entry. And these entries are going to be, you can think of each row, the non-zero entries in each row is corresponding to an edge. And once you pick a vertex, the corresponding matrix entry is going to be with the weight, incident weight. And the right-hand side, the column here, B, can be encoded as a function on the set of edges. And that's a more suitable formulation because we can, we will see that we can actually associate a topological space with this pair. In this formulation, an operator solution is going to be a function on the set of vertices to a unitary group. And once you evaluate it on the vertices, you will get these operators, and they are for each, if you specialize to a context, then they're going to be pairwise commuting, and they're going to be D-torsion. So that's what context means already. And the third property is that there's a linear constraint system. There's a linear constraint that's associated to the matrix equation. And it is essentially the matrix equation in the multiplicative form. So you have the incidence weight is going to be the powers of the operators, and you have a product. And on the right-hand side, you have the identity, and the tau function is going to appear as the power of this omega, where omega is the d power, d root of unity. So a linear constraint system is said to be a contextual one if it admits an operator solution over um for m greater than equal to 2, but it does not admit an operator solution over u1 that is a scalar solution. Such linear constraint systems are very interesting, and they're very important. Two examples here is Mermin square and Mermin star examples. So these are the hypergraphs where the dots here are the vertices and vertices of the hypergraph, and the lines are the the edges. So the tau function associates 0 to every context except these red ones. The red ones are associated to 1, are assigned 1. And an explicit operator solution for this linear constraint system is given by a 2-qubit Pauli's, as indicated here. So on the left-hand side, we have 2-qubit Pauli's. On the right-hand side, we have 3-qubit Pauli's. So the key idea is to first encode the hypergraph, the linear constraint system, essentially as using a topological ideas. So a topological realization for a hypergraph is a connected two-dimensional cell complex. Essentially, you think of the vertices as 1 cells and the edges as the 2 cells, and the attaching maps, they're going to encode the linear constraints up to a scalar. So essentially, you're ignoring the right-hand side of the linear constraints, and you're just considering the left-hand side. And that is going to appear later on when we take a quotient at some point, a quotient of the space of context. I will mention that at that point again. So these canonical examples turn into these tori with cellular decompositions given by in the pictures. So the top parts and the left and right parts are top and bottom, and left and right are identified. So you have a torus here in the picture, and similarly on the right hand side. The only difference is that they have different cell structures. So the idea is that the tau function essentially turns into a 2 cochain, because a 2 cochain is a function that associates numbers, in this case 0 and 1, to the cells. So you see the purple ones are the places where the tau function is 1. Otherwise, it's 0 elsewhere. So a function tau on the edges corresponds to a cohomology class because tau can be you can think of it as a 2 cochain. It turns out to be a 2 cocycle, and then you can have a cohomology class. And an important property here is that scalar solutions are detected by this class in the sense that a scalar solution exists if and only if the cohomology class is 0 for for any topological realization. And even more interestingly, you can say something that relates to the homotopy groups of the space. So if this linear constraint system admits an operator solution but no scalar solutions, that means it's contextual, then any topological realization has a non-trivial fundamental group. So you have this non-trivial loops in the topological realization. So if you think of the Mermin examples, you have this torus and you have these two loops which are non-contractible. So this is the essence, the source of the contextuality essentially, and that's in line with this statement. So it's more general, and the idea behind this theorem was to generalize Archipov's graph theoretic characterization of contextuality for d is equal to 2, and which only applies to certain hypergraphs. So this generalizes into one direction. So we have only characterization to one direction. So contextuality implies non-triviality of the fundamental group. So the inverse implication is open. So then you might say something in the reverse direction. So Archipov's characterization is restricted, but it tells you an if and only if statement instead of an if statement. So the question here is that so far, so this work has appeared as in joint work with Robert Rosandorf, and so far we have explained everything as which is everything related to the linear constraint system as a topological object, but the operator solutions are missing in the picture. So how can you interpret an operator solution in a topological way? So that's kind of the main idea of this talk. And so before that, we need to introduce a space of contexts. And similar constructions appeared elsewhere in the work of Adam and Gomez. So these spaces of this sort, they're called classifying spaces for commutativity. And here, the more natural name is to call it space of context, because the space BDM, which only depends on these two parameters D and M, so it's a cell complex consisting of whose n cells are given by n tuples of context. Essentially, if you think of them as group homomorphisms, it's more concise. So the n cells are given by group homomorphisms from z mod t to the power n to um. So these are contexts as we defined them. And if you unravel this definition, there's this geometric content here that is to be able to just say something about it. There's these pictures here. So in dimension 1, meaning that the one cells are pictured as lines like this, and then operator sits in this line or edge, and two cells are given by triangles, and a pair of operators like this determines the third one, because third one is the product. And the tetrahedron is going to correspond to 3 cells, and so on. So you have these commuting operators that are being attached to the edges, essentially. Well, a trivial case would be taking the m is equal to 1, which is looking at scalar context. So to say, these are contexts in the U1. Well, I can just talk about those things, because as we define them, contexts are just a bunch of unitaries. And in this case, it turns out to be this classifying space of this abelian group, the cyclic group generated by omega. So this cyclic group of order D. This is the ordinary classifying space, an object from algebraic topology. If you're familiar with it, you can think of these versions as non-commutative generalizations of this ordinary classifying space. So there's this quotient where the quotient appears. So I mentioned at some point that the topological realization actually doesn't see the right-hand side of the linear constraint system, meaning that we just looked at things up to scalars. And that's a natural space that can be obtained from this space of context is this classifying space for contextuality, which is a quotient. And instead of, so the quotient is as follows. So you look at the n tuples here, which are the n cells, and you identify 2 n cells whenever the matrices differ by a scalar in mu d. And that's essentially ignoring the scalars at each entry here. So this is a quotient space, and an operator solution can be turned into a map from a topological realization to this B-bar space. And this map can be defined more precisely, but I'm not going to define it here. It's defined up to homotopy. So here in the example of the Mermin square and the Mermin star, essentially putting up the operator solution, placing the operator solution on the edges, in effect gives you this map. Now, once you have an operator solution, you have a map, and if you have two operator solutions, you have two maps, and you can actually define an equivalence relation by saying that two of these operator solutions are equivalent if and only if the corresponding maps are homotopy equivalent. So the Mermin star and Mermin square is an example. So Mermin square on the left-hand side, if you add an identity on the right, you can think of it as a 3-qubit solution here. And this is the Mermin star. These two things can be seen as living inside this torus with a refined cell decomposition. And essentially, this refinement gives you a homotopy from this star to square. So if you look at the corresponding maps, Ft and Ft prime for the Mermin square star operator solutions, both are 3 qubits in this case. It is going to be a map from S1 cross S1, which is a topologist way of writing a torus, to B bar space, and the parameters dm, d is equal to 2 and m is equal to 2 cube, because we have qubits here, 3 qubits here. These are 3 qubit solutions. And we have this homotopy, meaning that these operator solutions are essentially the same, equivalent. And so essentially, I mean, computing this homotopy classes of these maps amounts to classifying the operator solutions because they're equivalence classes. And such homotopy classes are hard to compute, even though this space is two-dimensional. It turns out it boils down to understanding the homotopy groups of this space. But in general, we don't know the homotopy groups of this space. But there's a way around this problem, which looks as if it's making things more complicated, but it's actually not making things more complicated, as we will see. Instead of looking at a unitary group at a fixed dimension m, we can consider all the unitaries by including um into um plus 1, by including an 1 on the far corner here, and then taking the union of these unitaries, which the union is going to be called a stable unitary group U infinity. On the space of levels, we can do a similar thing for the spaces. Remember that these spaces are constructed from context, so you can take a context in um, send it to a context in um plus 1 via this map, and then take the union of these spaces, and at the end we are going to obtain a space which doesn't depend on m, so it's BD infinity. Essentially, this is what we want to understand. So we want to change this target here with a quotient of this space. But the quotient is going to be a little problematic. I will come to that. First, let's try to understand this space before going to the quotient. So this space can be understood by passing to projectors. So any context give rise to a projective measurement, essentially by simultaneously diagonalizing these matrices because they're pairwise commuting. So pi is a function here which sends an n-tuple of numbers here to the projector onto the intersection of these eigenspaces. And each of these eigenspaces are associated to a certain eigenvalue, and the eigenvalue is given by a power of omega. So the stabilization procedure essentially takes these projectors here for a fixed dimension Cm, and then considers all finite dimensional projectors on C infinity. So you're essentially looking at finite dimensional subspaces here of C infinity, or the projectors associated to that. So that's what this object means. And that is essentially the stabilization process in the projector picture. So why did we pass the projectors? Essentially, the reason is that there's a connection to gamma spaces. So gamma space is an object introduced by Siegel in algebraic topology to study certain stable spaces, which are called spectra, and also to define generalized cohomology theories. So after stabilization and passing to the projectors and then imposing the partial sum, so this partial sum is going to be important. So if you have two projectors which are orthogonal, then you can take the direct sum and get another projector. So this is an operation on the level of projectors, and this operation is implemented by the definition of a gamma space. So I'm not telling you what the gamma space is, but essentially this partial operation is the key point. So it is a functor. You can see gamma spaces as functors. So they are the collection of spaces indexed by natural numbers n. So here we have these functions into these projectors. And there is a compatibility between different n's. And in this compatibility is essentially a little bit more richer than the structure of a simplicial space that's, or the cell complexes that I have described. Essentially this be the infinity, the finite versions. They're obtained by gluing these spaces, and the gamma space sees more structure in these objects, and that's essentially the reason we pass to projectors, because there's already a theory that explains how to study these spaces. Now, every gamma space gives a cohomology theory. There's a recipe for that, which is explained by Siegel. And once we pass from this stable space to this K mu D, which is the gamma space of projectors, then we can actually compute everything about this space, all the homotopy groups and everything. Well, so we come to the other space, which is the main space. So this was the space without the bar. And this space is a space of contexts. And this space is a space for contextuality. And so a generalized cohomology theory we will use to label the operator solutions. It is going to be obtained from K mu D. So this is a generalized cohomology theory coming from the gamma space, but we want to actually remember the operator solutions are maps into this B bar. So remember that B bar is a quotient of B space, and K mu D is associated to this space. So that's essentially the same thing. So the generalized cohomology is on the right-hand side. You can also take a quotient, some sort of quotient in a suitable category. And that quotient is going to give you another generalized cohomology theory, which behaves like a stabilization of this B bar space. So yeah, the stabilization of the B bar space is not as direct as the BDM space, because the stabilization maps, they don't really descend to B bar. And you have to go through this taking the quotient in a different category. But anyway, so here this generalized cohomology theory exists by some techniques from stable homotopy theory, and the goal here, what we have achieved, is that you can compute everything about this cohomology theory, whereas we were not able to compute the homotopy on the left-hand side. So for a connected two-dimensional cell complex, for example, a topological realization, the CDM cohomology of a space is given by a direct sum. So there are two copies here of the H1 and H2 of the space in coefficients ZDM. And ZDM here integers modulo the greatest common divisor of these two numbers. So application here for a linear constraint system, we have an H and tau and T. T is the operator solution. As we have seen, there's a procedure to turn this into a map into classifying space for contextuality. And once you construct a topological realization for the hypergraph, and then stabilization gives you a class in the CDM cohomology of this topological realization. So this result tells us that there are two parts. There's H1, H2, so I'll call it phi1 and phi2. So phi2 is a two-dimensional cohomology class, and there's a connection between phi2 and tau here. So tau is the cohomology class associated to the function determines the linear constraint system. This is closely related to phi2. So there's a connection between the two when m is a power of d. That's the case. So for example, if d and m are coprime, then every linear constraint system admits an operator solution that admits an operator solution over um, admits a scalar solution, because once you have the d and m are coprime, then we have everything on the right-hand side here about the CDM cohomology, which determines the CDM cohomology. On the right-hand side, everything is going to be 0, because z modulo dm, when d and m is equal to 1, is going to be 0. So everything on the right-hand side is 0. That means the CDM cohomology is 0. And that implies that the tau cohomology class is 0, because the reason here I said this tau is connected to this phi2 class, and this is 0, and this is 0. And this being 0 means that there's a scalar solution. So that's there's a different way of proving this result, but immediately falls from this computation of the CDM cohomology of a space. So that's why I'm presenting this. So let's go to the Mermin class. So an operator solution for the Mermin class given by Mermin square given by the standard operator solution, which is a 2-qubit one. You can always include an identity, tensor with an identity, and then lift it to an n-qubit solution. So here I'm going to keep n just greater or equal to 2. And the CDM cohomology in this case of the torus, remember that the topological realization is a torus in this case, is going to be the H1 of the torus and H2 of the torus. So the greatest common divisor of these two numbers is 2. So the coefficient is Z mod 2. So H1 of the torus is Z mod 2 square, which is generated by the two loops, non-contractible loops, and H2 of the torus is just a copy of C2, Z mod 2. So if you ask the question, what does the corresponding class in here that comes from the operator solution of the Mermin square, then it requires a computation. It turns out that the Mermin square, which I will denote by capital M, corresponds to the class here given by 0, 0, 1. So the first part here coming from H1 is 0, and the second part corresponding to H3 is 1. So that is the significant indication that that's a contextual one, because the second cohomology here appearing is non-zero. So we can interpret, so we can ask how can we interpret the operator solution. So we are here, the cohomology classes in the generalized cohomology, theory. So we see this particular class in here, 001, is coming from the Mermin square. So you can ask, what about the other classes? Or more generally, if you change the parameters to d g to power n, but this is sort of the canonical case where we have a Hilbert space, which is an n-fold tensor product of c to power d. Then again, the greatest common divisor is z mod d. So you have these same coefficients here. Essentially, you're looking at the h1 and h2 of the space. And when d is equal to 2, an odd number, the right-hand side is always computable. It's a simple thing to compute the h1 and h2 of a space. And that means there are something here. These are stable classes. And are they coming from linear constraint systems? So there's a rephrasing of the question that I asked in the beginning of the talk for odd local dimension. So you can go backwards. You know the state classes here, and then you can try to construct representatives in terms of linear constraint operator solutions of linear constraint systems. So there's a parallel here to SPT phases. So these are symmetric product topological phases. So the idea is more clear if you pass from complex numbers to real numbers. So you just do everything in the real numbers. Instead of complex vector spaces, use real vector spaces and so on. So you can show that there's a cohomology class, which is CR dm, or 2 to the power m here. That's what we are looking at. There's only one case in this real situation. So there's a real version of CDM cohomology. When you apply it to a two-sphere, then there are two parts. So there's one part, Z mod 2, that comes from the Mermin square operator solution, which you think of it as a orthogonal matrix, solution in the orthogonal matrix 4 by 4. And there's another part here, which comes from an SPT phase due to Gu and Wen. So this is a fermionic SPT phase that you can show is captured by this cohomology class. So to be able to show that, you need to work on the stable homotopy side rather than the lattice model side. So the parallel here that I was going to tell you is that the operator solutions and stable classes, and this SPT case, you have these lattice models and the stable classes. You have the similar problem of going one way to the other or backwards. So the interesting second point here is that these cohomology theory captures two things: linear constraint systems on one side and SPT phases on the other side. So they're combined in one picture. So one can ask interesting questions. So what are these connections? Are there other connections between these two things where linear constraint systems and SPT phases appear together? So there's this computational value of these contextuality and SPT phases. That's another connection, and one can ask questions around these ideas, if a stable homotopy theory plays a role in computation somehow. So of course, these are very vague questions at this point. So thank you very much for your attention.